Whoa, like it isn't hard enough already. So, good afternoon. I've really been looking forward to this event. I was here last year, and it was one of the best events of the year. I like the speakers. I like the audience. I like that we have 50.4% female speakers this year. Yeah, that's incredible. I mean, like, just look at the Wi-Fi password. Yeah, so I think that's impressive, and it's good. A few years ago, maybe 3 years ago, I would have been embarrassed having this headline on my slide because it's a bit it feels a bit crazy 3 years ago, maybe even 2 years ago. But I must admit that I'm coming to the point where I'm sort of giving up and saying, maybe we are actually on the road to sort of real artificial general intelligence. And that's what I'm going to talk a bit about today. So, as you heard, I've done machine learning at Uber and at Amazon, and the whole world sort of has been catching up with me, we are now calling all this artificial intelligence. So I start thinking a bit about so what is it that I have been doing in the past with virtual assistants and all that stuff? How much artificial intelligence is in that, and is that actually artificial intelligence? Can I point to that and say, that's what it is, yeah? So if you think about Siri and Alexa, fantastic technologies, yeah? I spent 8 years trying to build things like that when the recognition ratio on a phone was about 80%, yeah? Sounds high. Well, 1 out of 5 words are completely misinterpreted, yeah? So you can say no, and it says yes, or here's yes, and things like that, yeah? So speech recognition has improved incredibly. It is deep learning have done that, LSTM, recurrent networks, just fantastic technology, text-to-speech, generative nets, WaveNet from DeepMind, etc. It's like all incredible technologies. But to me, it's like, it doesn't really make Siri and Alexa particularly intelligent when I interact with them, yeah? It's all canned anyway, yeah? So, Amazon, Netflix recommendations, everybody's so fascinated by the old Netflix challenge and all that. A lot of very deep stuff going in there, deep learned representation learning, deep learned embeddings. But again, it's really just to recommend some products on Amazon and some movies. And again, despite all the technology, it doesn't appear to me to be a good example of intelligence, yeah? Fraud detection, anomaly detection, incredible technologies again, but not particularly representative of what we call intelligence. Equity trading, we see great use of deep learning in trying to figure out important signals. The trading desks are being cleaned for human traders and increasingly taken over by systems that perform much, much better. They're really good at detecting trends from tens of thousands of sources of news and other information. So, but hardly, trading is hardly what I think about as intelligence either. The Facebook feed, I think I should skip that one for today. And eventually, we are going to talk about job titles, yeah? That's at least where artificial intelligence is really showing up, yeah? Every other job title on LinkedIn now, which is incredible. So I really ask myself, what is real intelligence, yeah? So I look up the dictionary because that must be where I find the answer, and it's something about, acquiring and applying knowledge and skills. I'm like, I don't know what that means either. It's too abstract for me. So what is real intelligence, yeah? Where do we see it? Well, what is the only real intelligence we know? That's the stuff in biological systems, yeah? So we have to look at them. We have to see, what's going on there? And if you really look at it, there may be a nature on some planet out there that doesn't need intelligence, yeah? Because they don't really operate by 4 principles. The first one of them is that living things has to consume energy, to deal with entropy, yeah? So whether it's a plant in the sun, or it's a mouse or a rabbit or whatever, we all need to eat. Yeah? We need to consume energy to maintain who we are, what we are. Yeah? And while we're doing that, we have to avoid getting eaten. Yeah? That's very, very important. Yeah? Super important. Yeah? So we need something to do these two things. Yeah? And also we need this lecture we're going to take another day. I'm not going to do that now. And then we are going to constantly be aware of physics. Yeah? Because we live in a physical world where inertia and gravity and the big boulder coming rolling, or the heavy vehicle coming against us, or the big foot on the ant, stuff like that, we have to watch out for physics. Yeah? So those four things are the things that actually leads to a demand for intelligence. Yeah? So that's really interesting. Yeah? It's not Netflix recommendations or things like that. Yes? It's these four things that drive that. So we need to look at that, we need to look closer at that, and there's a lot to be learned there. Yeah? So I haven't talked about neural networks yet, but it's close. Yeah? Because to do intelligence, we need infrastructure. Yeah? Nature has implemented infrastructure for us and our fellow lively things. It's in the form of chemical mechanisms. It's in the form of cellular structures to put the chemistry inside some boundaries so it just doesn't get too diluted. It's multicellular organisms with messaging systems and specialization so that certain cells are doing certain things, and because they are sort of diverse or specialized, they need to communicate with each other. And sort of through evolution, nature also created things like our ability to feel touch, to see, hear, taste, smell. Everybody says we have 5 senses, but then when I started Wikipedia this and read a little more about it, it turns out we have many more. We have the senses of balance. We have a sense of motion, hot and cold, temperature, and some other animals like pigeons and was that sea turtles I saw the other day? They have actually can feel magnetic fields. So nature seems to have invented what I saw, last number was 21 different kinds of sensors. Yeah? So it's interesting that we have sensors and we have sort of some networks that make things smart. Yeah? And when I talk about intelligence, bear with me, it's an ant, it's a bee, it's a rabbit, it's a human. This is all levels of intelligence, yeah? But it's all derived out of this constant need for surviving in the world with those 4 principles, yeah? So if you think about it, if I want to do something really interesting with this, think about it as a biodome, yeah? A closed ecosystem where there's something going on in there. That's sort of how I want to do my intelligence research now, yeah? And what is better than taking a real-time 3D engine, yeah? So the 3D thing, that's the spatial thing, yeah? The real-time is a physical world, yeah? Time, gravity, inertia, you have all the physics in there, yeah? And that is actually this controlled, self-sufficient ecosystem. Yeah? Think about the biodome. Yeah? You spin up this real-time 3D environment, call it a game engine, call it what you want. You spin it up, and you have something that actually really, really closely replicates the real world. Yeah? So I really want to think about the work we've done at Unity as creating your private AI biodome. Yeah? So we've created something we call Unity ML agents, which is essentially some software, it's open source, that allow you to explore those 4 principles that I mentioned to you. Because in a game engine, you have your private biodome. Yeah? You have all those 4 principles. You have them in a Pac-Man game, yeah? You move around and someone wants to eat you, things like that, yeah? So that's what I'm going to talk a bit about and introduce you to. These machine learning or AI training environments are not exactly something new. They have been around for at least a couple of years, yeah? So they are actually relatively new. But DeepMind has sort of Deep Lab, there's OpenAI, there's the Allen Institute in Seattle. There are, few places they have created these environments where you can explore certain aspects of what I talked about, yeah? So you can explore like visual challenges, yeah? So you can use a lot of convolutional network technology, and you can learn how to solve visual challenges in these environments. Yeah, so that some of them are focused on that, finding your way through a maze or something like that by looking. Yeah. Other environments are focused on physical and physics and accuracy in movements and geometry. Yeah. So those environments, you have seen some of those videos of strange stick persons learning to walk and things like that. So in those systems, physics matters a lot, and what you're trying to solve is this physical problem of learning to walk or climb or jump or do something or dance or whatever, yeah? The third class of environments are the cognitive environments. AlphaZero or AlphaGo comes to mind there. You have to watch that movie on Netflix if you have not. Have to watch it. AlphaGo comes to mind because that's a cognitive problem. Yeah, there's no interesting physics in it. It's really there's no interesting graphics in it beyond its 19 by 19 pixel field of black and white and nothing. But it's not very challenging. But cognitive, oh my God, it's a really big deal. Yeah, solving the Go problem is actually bigger than most people think. It's actually really big. Okay? And we can use that technology in a number of other areas of great interest to humanity. So when we take the Unity ecosystem, yeah, so we have about 60% world market share in game development. So about 60% of games on the market is developed on Unity. When Xbox, they launched the latest Xbox, 6 out of 7 games for Xbox was written in Unity. We have 80% market share in VR, all that stuff, yeah? There's a reason, because it's sort of easy to develop stuff in Unity, and you have all these kind of very sexy, wonderful looking, complex environments that you can create with that, yeah? So you're kind of not really limited to solving just a graphical problem, or just a physical problem, or just a cognitive problem, yeah? You can imagine putting all those together, and now the AI you have to develop here needs to deal with all those things, yeah? And that comes very, very close to what has challenged living animals, humans, in nature, yeah? So I want to add to that, because it doesn't become AI by just, writing a game or writing some game environment where you have game objects, yeah? You need to take nature's learning method. There are several methods. I'm just going to pick one today. Yeah. There are evolution also. There's also imitation learning, and there are other methods too. But I'll take one that we support directly, and that's reinforcement. And it's basically the idea that in such an environment, you observe, you take actions, and you look at the rewards, and it cycles around, and there's nobody interacting here. There's no human in the loop, yeah? It just keeps learning and goes from exploring to exploiting. I'm very quickly going to show you my chicken video. I think I showed that last year too, but I just want to make sure that you get the point. It's basically, can a computer system learn to enable the chicken to cross the street, yeah? And the chicken is basically just looking at the pixels. It's 4 actions: go left, right, forward, backward. And the reward signal is like negative for getting hit by a car and positive for picking up a gift package, yeah? And that's it. And when you let a reinforcement learning system look at that, it will start out knowing nothing. It's tabula rasa. It's a clean slate. It has no idea. But in a moment, it will hit one gift package, and then after that, it will get killed. Yep, right there. So it learned 2 things within 10 seconds. That's actually 2 pieces of information, yeah? Very quickly, after some training, it can actually go and collect these packages and avoid a few cars on the way. Not really great yet, but it's pretty good. Imagine, you have to remember, it has learned everything here, yeah, from scratch, yeah. And after 6 hours, it gets really good at it, yeah. It becomes superhuman, yeah. And the other day I showed this to someone, yeah. Yeah, gets really good, yeah. I showed this to someone the other day, yeah, and they asked, "Hey, I got you know, you're cheating, because you told me it doesn't really know anything about forward or backward. You saw early on when it was running around, it ran more backwards than forwards, yeah." So he said, "Well, it does know that it needs to move forward." And I'm like, no, it does not. Only thing it knows is that there are more gift packages in the future than in the past. So it also learned that little thing that I never tell it to cross the road. Yeah, I just say, go and get gift packages and don't get killed. And it keeps running. Because why would it run the other way? Because there are fewer gift packages there than there. So what I want you to think is that it's a fairly simple algorithm, this algorithm, yeah? Yet it figures out certain things that I think they are almost strategic, yeah? It does learn this, and we tend to sort of forget it. But there's a lot of important details here, yeah? So we're making this available, open source. Students, researchers, developers can play with this. You create the environment. It could be the chicken environment, yeah? You train it, and then the model you get out of it, you shove it inside your game, and you'll now run on an Xbox, on an Android, on an iPhone, or in your VR thing. You will now have that intelligence with you in the game, yeah? And we have created a bunch of environments, 12 environments at this point. I show you the balancing ball. It's a pad balancing a ball. The penalty, reward penalty is if the ball falls down, that's negative, yeah? And in 30 seconds, it learns to balance the ball. Yeah? No coding, no algorithms, no nothing. Just use the chicken algorithm and it learns to balance the ball, yeah? Yeah? I want to show you this other one. Jump the wall. Jump the wall, but you can't jump it directly because you can't jump that high. See what it figures out? It figures out to push the big cube. Use physics, yeah? Again, there's no coding here. It's just the chicken algorithm again, yeah? It figures out to push the cube next to the wall, jump on the cube, jump over the wall, and you're done, yeah? You get a positive reward, yeah? So it uses physics because it uses collision in the game, yeah? But again, it's not, I don't program this, it just figures it out. There are the physics law in there. If a little object pushes the big object, it will move, yeah? There's another fascinating thing here, which is that the little cube cannot learn this right away. So what we did is that we made a very low wall, and then we raised the wall, you know, half an inch every time. It graduates, yeah? It goes through like 5 grades, and it gets really good at it. It will learn it directly. It will take much longer time, and it will never be as good as if it goes through what we call curriculum learning. So basically, stepwise improvement, yeah? So the chicken algorithm I showed you also has this strange other thing that it needs to go to school, yeah? Like in 1st grade, 2nd grade, 3rd grade. Anyone who tried to skip grades, and there may be some of you here who skip grades, but it's tough, yeah? Okay? There's this other example. Normal reinforcement learning will not be able to do this. So we have a little addition here. Blue guy comes in, he looks at the big cube. The big cube is either orange or red. Depending on the color, orange or red, it needs to pick the right exit, yeah? Red cube, red exit, orange cube, orange exit, yeah? Again, it's the chicken algorithm, doesn't know much, but we slammed another thing in there. We slammed the ability to remember, memory. For the tech guys, LSTM, long short-term memory. Put that in there. That's all we did, yeah? Now what it does is that it learns, we don't even tell it that color is important. We just give it eyes, yeah? So it sees shapes and geometry and stuff like that. It learns that if I somehow take note of the color and I let that information bubble through the neural net, as I move beyond the first cube. And I don't see the cube any longer, yeah? I don't know what color it has because I'm not looking at it, yeah? It learns to remember the color and pick the right exit, yeah? So you give it a piece of working memory, it uses it. We don't say, see the cube, register the color, move on, yeah? Don't say that. We actually just let it try and try and try, and it learns what memory matters. What should it memorize, yeah? The last example, let's see, there we go. The soccer example is also very interesting. 2 players. One player is being rewarded for scoring at the other end, and one player is being rewarded having a negative reward for scoring on it. Yeah. So one for scoring, that becomes what you recognize as a striker in soccer. The other one becomes clearly a goalie. Yeah. So the way you train this system is that you actually, and we don't tell them to be goalies or strikers, yeah? We give them rewards, and they become goalies, yeah? And they behave like goalies, yeah? I didn't tell them to stand in front of the goal. That's just what they learn, yeah? Interesting enough, in this one we train the striker alone. Striker gets really good at scoring, and then we put in the goalie, the defensive player. The striker now is being challenged, because the defensive player is in there, but actually initially the defensive player will just move around and waste time. Yeah? But figure out eventually, like the chicken, I need to stand in the goal and I need to protect the goal. And what happens now is that first train the striker, then train them together, and they both get better and better and better until you're done. Then we clone them and create 2 teams and put them in and play against each other. Yeah? And not a single line of code. Yeah? I think this is very important. Not a single line of code in all this, yeah? So we have open sourced this, go and download it. We have had a lot of use already of this. I don't think that machine learning, I don't think that AI and reinforcement learning should be for a few big corporations. I think that this stuff is safest in the hands of the many. So that's why we're doing this. We make some of the algorithms from DeepMind and OpenAI, we basically make them available. So when you download this, you get those algorithm implementations with it. And we really think that it's important to democratize AI and get as many people to put their hands on it, especially this stuff that's a little beyond your next movie recommendation or getting an Uber on time, which is sort of, more practical problems. But I think that that we are really on the road to something very interesting. I think that biology has a great trip in store for us. I want to mention a few things. Attention. We are built with attention. We don't see everything in the room, and you don't process everything all the time, yeah? An Uber vehicle has about 600 sensors, and they're all being processed, yeah? Even when it's not important, yeah? That's why you have a big computer in the trunk, yeah, or many computers in the trunk, yeah. If I'm going to use AI in a handheld game on a phone, I actually live by the same limitations as nature, yeah. This 20 watts processor cannot be this big, yeah. My battery cannot be that big, yeah. So I have to implement things like attention, where I learn not to recognize everything I see, but just the thing that matters, yeah. Number one, learning from, when you do AR, things like that, and people segmentize the whole image. It's like, segmentize what is important, ignore the rest, yeah? The other thing is episodic memory. My oldest child, when he got 2 years, we made him lay a birthday cake, 2 candles in. I get down with the camera, and just as I flash, he put his finger in the fire, and I have this scream. I have the picture, and he didn't want me to show it for you guys. He would be embarrassed because he's now a grown-up. But he never did that again. He'd done many other things, stupid things, yeah? Yeah? But he never put his finger in the flame ever again, yeah? Yeah? He broke his legs last week, his legs skiing in Tahoe, and I said to him, dude, did you learn anything from that? One-shot learning. He said, oh, it was my best run ever. I'm like, I give up. So episodic memory is like, it's one-shot learning. Yeah? Do I always need 1 million attempts to learn? No. So what do I need to do? I need to develop machine learning that learns what to take note of and what not to take note of. Yeah? Working memory, I showed you that. Yeah? working memory is sort of, I remember stuff, but if it gets further and further behind, I start forgetting it, yeah? That's how we work too, yeah? Then we play board games. We can remember some moves, but not all of them, yeah? And continuous learning is very, very interesting too. Is this thing of I learn one thing and then I also learn another thing, but a lot of systems tend to forget what they learned first, yeah? We have in biology, there's sort of some plasticity in the neurons that they don't reconfigure that easily. And if it's important what you learned in the past, it sort of sticks around, yeah? So you don't forget, yeah? And last thing I want to mention is I saw an article in ACM, IEEE saying computers don't dream, and I'm like, oh, whoa, stop. Yeah, computers do dream, yeah. Dreaming is basically simulating, generating enormous amount of scenarios and learn from them, yeah. This is like what AlphaZero, AlphaGo is doing, yeah, for example, yeah. Monte Carlo tree search. That is, you go in, you prepare for a job interview, yeah? All night you can't really sleep because your brain is running through all these questions they are going to ask you, yeah? And then you come into the interview and they never ask you those questions, yeah? But you do really well anyway because your brain built actually a model that is general and sort of prepared you for all the nuances, yeah? By simulating. This is what we do when we run game situations over and over and over in all kinds of variations and train a model, and the model can deal like the chicken. When the chicken runs, everything it sees for the first time. Yeah? Yeah? It has never seen these episodes. The cars are coming in randomly, yeah? Complete random function, yeah? But it has seen enough at that point to sort of generally know how to survive. Yeah? So this is what we're doing too. Computers, they dream too. Yeah? So that was it. I hope that you understand there is a, when you look at this, it can, an Uber self-driving car should pay attention, yeah? It should see important things and maybe ignore less important things, yeah? Your software and your phone should not process everything, but only what really matters, yeah? So a lot of the things, I know you're watching that video instead and listening to me. So a lot of the things I said is sort of pushing the boundaries, and I do think we're going to get there one day. But yeah, talk about attention here, yeah? It's just paying attention to the handle. It doesn't register anything else. It doesn't see anything else, yeah? So think a lot about what I said is that it's actually applicable to all kinds of real-world situations, yeah? Whether you're building personalized systems or you're trying, attention is like in NLP. You don't read what's before the sentence and after the sentence. You only read the sentence, yeah? And then you read the next sentence, yeah? So a lot of what I said is really applicable to very, very industrial and enterprise applications that we see around us. Okay, I ran over time. I apologize. Thank you. Thank you.
Thank you, Danny. That was awesome.
Thank you for having me.
Can I ask the team to join me on stage? So how's the day been so far? Good? All right, I'm glad you guys were able to stay this late. A lot of you guys have asked, like, what does it take to put an event together like this? And this is it took 9 months of effort from a large team who were extremely, extremely busy people. So if you guys would like, join me in appreciating and recognizing the part of the team who helped put this event together.